So welcome to this third video in the AMC 10 problem solving series. Today we're going to be tackling some issues with complex numbers, as you can see, and the first problem tells us to simplify this complex fraction. Now we're going to approach complex fractions just like we approach fractions which have radicals underneath them. What we're going to try to do is use our knowledge of imaginary numbers. We know that I is equal to the square root of -1, and we know that I squared is equal to just -1. So we can use that knowledge to simplify the denominators of fractions which have imaginary numbers or complex numbers. Now, what do I mean when I say that we're going to treat imaginary or complex numbers just the same way we treat radicals? Well, what I mean is that first thing we're going to do is, well, let's write this a bit bigger. We have this fraction, 1 plus I divided by 3 minus I. The first thing we're going to do is multiply this fraction by its conjugate, which is going to be 3 plus I. As you remember from the last video, the conjugate helps us use the difference of squares property to help eliminate any middle terms and make sure that there's no imaginary numbers or radicals remaining in the denominator. Okay, so we're going to go ahead and multiply this, 1 plus I times 3 plus I. This is just simple distributive property right here. Now here, as you remember, we're going to use the difference of squares. So we're going to take the square of the first term, which is 3 squared, which is 9, minus the square of the second term, I squared. Now remember that I squared is simply -1. So this is going to be -1. Negative, that's going to give us a +1. And 9 plus 1 is going to give us 10. Now, we're going to, as I said, use the distributive property to simplify this out. We get 1 times 3 plus I, which is just going to be 3 plus I, plus I times 3 plus I, all divided by 10. Okay, we're gonna go ahead and simplify this. So 1 times 3 plus I is just gonna give us 3 plus I, and I times 3 plus I is going to be, well, I times 3 is 3I, and I times I is I squared. Okay, and we're gonna go ahead and divide this by 10. I squared is -1. 3 minus 1, that's going to give us a 2. Let's bring this over here. 3 minus 1 is going to give us a 2. I plus 3I, that's 4I right there. Why don't we factor out a 2 just for even more simplification measures? So that we get 2 parentheses 1 plus, well, 4 divided by 2 is 2. So we're going to write 2I divided by 10. And what factoring helps us do is we can cancel this out so that instead of having 10 in the denominator, we just have a whole number of 5. And that's going to be our final answer. Let's take a look at what we did. First of all, we took the fraction 1 plus I divided by 3 minus I, and we treated the imaginary numbers just like radicals, because that's exactly what they are. So we multiplied this fraction by its conjugate so that we could use the difference of squares property for two main reasons. First of all, it helps us eliminate this imaginary number by turning it into an I squared, and it also helps eliminate any middle terms. And then we simplified through, we foiled through, if you like, foil, and we simplified, and there you go, voila. Second question: if A, B, C, and D are real numbers, find the real components of A plus BI times C plus DI. Now, let's first remind ourselves what we mean by the real component. Well, if you have your standard complex number, A plus BI, and you take its real component, what we're actually doing is we're not taking we're just taking this A right here, right? So that's going to be the real component of this complex number. So when we ask ourselves to find the real component of the product of two complex numbers, we of course have to distribute out these two terms and find out what happens, what our product will be. So first of all, let's be a bit careful. We're going to multiply a by this whole term, c plus di, and we're going to add that to bi times, once again, this whole term, c plus di. Okay, now we're going to go ahead and simplify this just by pure distributive property. I don't need all of this. So this is going to be the real component of a times c is ac plus a di plus, that's not a plus sign, okay, plus bi times c is going to give us bic plus bi times di is going to give us bdi squared. Now, now go ahead, take a look at that, and once we simplify that, hopefully we're going to find ourselves the real component. So let's bring this over here. The real component of, well, first of all, we have I squared at this end, so we can simplify that perhaps. This you can write as bci, so that we can factor out the i's here, and we can get ac plus I AD plus BC minus BD. Okay, now you find out that this is the imaginary part of this complex number, and our real part, our real component of this complex number will thus be AC minus BD, and that will be the final answer for this question. Now let's take a look at what we did once again. The question asks us to find the real component of the product of two complex numbers. So of course, we found out what the product would be by simplifying using the distributive property, or FOIL if that's what you like. And we found out that this was the product. We factored out the I so that we would know which part of the complex number were imaginary and which parts were real. And we found out that this part was the imaginary part, and AC minus BD were the real components of this complex number. Okay, so let's move on to the third question, which asks us 1 plus I to the 4th power times 2 minus 2i to the 3rd power. So what's our final product going to be? Well, this may seem like a loaded question at first, and kind of seems like it is. So the first thing I'm going to try to do is see if there's a way out. Well, the first thing you can do is just bash it out. Just use brute force to find, you know, what is 1 plus I to the 4th? What is 2 minus 2i to the 3rd? But let's try to see if there's any pattern, any tricks. Let's just find what 1 plus I times 2 minus 2i is. Okay, let's test this out first. Alright, so this is going to give us 1 times this whole term, which is 2 minus 2i, plus I times 2 minus 2i. Alright, let's simplify this out. Plus I times 2 is going to give us 2i minus 2i squared. And already you see that there's a catch. This minus 2i and this plus 2i, gone. This 2 minus 2i squared. We have an I squared. We are so lucky because I squared, if you remember, I is negative 1. Square root of negative 1. So if we square I, we're just going to get negative 1. So this is going to give us 2 plus 2. What an amazement. Now we can solve this problem much faster, because we know that the product of this term and this term is simply 4. They're just multiplied by each other a different amount of times. So let's use that to our advantage. So we know that this whole thing is going to be 4. It's going to have a product of 4. And let's try to pair this up. So we have 1 plus I times 2 minus 2I. So there's 3 of this, and then there's finally a lonely 1 plus I. So these two terms are perfectly paired 3 times in a row. So since we know the product of multiplying them once is 4, we're going to cube that product so that we can find out what the product of them multiplied by themselves 3 times is. And we're going to multiply that by 1 plus I. So 4 cubed is 64. 4 times 4 is 16, times 4 is 64, times 1 plus I. And now the problem has become trivial. Our final answer is 64 plus 64i. Now I hope I haven't confused you right there. Now what I did was, instead of calculating what 1 plus I to the 4th is, what I did was kind of pair up these two terms. And when I paired them up, I found that when you multiply these two terms by themselves one time, you get a product of 4. So when you multiply these two terms by themselves 3 times, you'll get a product of 64, and then have this 1 plus I remaining. Because remember, this 1 plus I is raised to an exponent that's 1 more than the other term. So that's how we got our answer for the third one. Thanks for watching, and I'll see you in the next one.